All right, first of all, thank you. It's a delight to talk to a very varied audience. So I've planned this talk to address students, teachers who have interests across disciplines. So if it's too basic for you, I apologize, but hopefully towards the end you will see where I'm going with this. The focus of my talk will be to give you a flavor of the kinds of techniques we would use to study something like the first stars. And towards the end, I will get to the part where I will discuss the work that we do at RRI about this. So let's start with having some common ground about what is a star. I think we all have an intuition of what a star is, and most of us in this audience know that there is something about nuclear fusion, hydrogen, helium, something, right? There is a governing body, a consortium, if you call it that, called International Astronomical Union, IAU. They were the guys who kind of kicked Pluto out of the 9 planets, right? So they have a definition of what a star is. I'm just going to paraphrase to my best memory, okay? So it is a spheroidal plasma, a luminous spheroidal plasma that it holds itself together with gravity, sustained by nuclear fusion at its core, okay? That is a all-encompassing definition of what a star is. But we know, if you look out into the night sky, hopefully outside Bangalore somewhere on a highway, you see a bunch of dots that are bright, and we know those are stars. We also know that the sun is a star, okay? And stars have different classifications. We won't go into that today. But for the most part, what we call in astrophysics parlance a main sequence star burns hydrogen through nuclear fusion to give you helium. So once it burns all of its hydrogen to helium, the helium burns to carbon, carbon to iron, and there are a bunch of processes. Some stars explode in supernovae, some become something called brown dwarfs. There are different kinds of stars, okay? But that's what a star is for all practical purposes today, okay? Now, here are some numbers that just to get you thinking, okay? We have different measurements, including something I'll discuss later, that have told us that the present age of the universe is about 13.8 billion years, okay? So we also think our sun is about 4.8 billion years old, okay? Which means that the sun was born at some point of time in the history of the universe, right? That's common sense logic, which means that the sun and the universe are not of the same age, right? And the sun and maybe stars older than the sun were born even earlier. Okay, so now I hope we agree that stars are born. They have not always existed. So first question, how do you think we know the age of the sun to be about 4.8 billion years old? I gave you all the answers to get the question, right, to this question. We know how much hydrogen has been burnt into helium if you take a spectrum of the sun. That's just one technique. We can also estimate typically the age of the solar system, okay, by looking at, for example, moon rocks and seeing some radioisotope measurements, like how we do carbon dating on Earth. We can do other radioisotope dating of different parts of the solar system. Earth is a little problematic unless you go deep into the core because there's a lot of other contamination, right? So we have found a way to get the age of the sun, okay? Now, with a lot of the measurements through several years and a lot of theory, we have arrived as a community in astrophysics. For the most part, we agree. There are some exceptions that we live in a universe that we call as part of a standard cosmological model. Okay, in technical parlance, we call it the lambda or dark energy cold dark matter, lambda CDM model. Okay, in this model, at some point, we don't know exactly what happened, and that's a big question mark. The universe starts, okay? There is a T0 in some singularity. In popular language, that's called the Big Bang, okay? We don't really think there was a bang. It was not an explosion defined in space and time at one point that expands. Everything starts at that point, okay? So let's not try to think about what was behind that point. At some T0, your clock starts ticking. Within the first few minutes, all the matter that you and I are made up of today, like all the atoms you think of, this table, laptop, all the particles, we call them as baryonic matter, okay? The type of matter we don't understand but we think is out there is something called as dark matter, okay? There's something else called dark energy, and there is energy like you and I understand it, right? Heat, light, right? So we'll call that energy. So the universe is filled with dark matter, keep that aside, dark energy, keep that aside, but we know there were baryonic particles, okay, and light the way you and I understand it, okay. This baryonic matter is very, very hot. It is a plasma, okay, because the universe has started out in a very compact place, okay. So the baryonic matter exists as protons, electrons, some helium nuclei, okay, little bit of lithium somewhere, and that's pretty much it. So the early universe had only compositions of hydrogen and helium, but it was not in the form of an atom, it was in the form of ionized plasma, okay. And the light or the energy kept bouncing off of these ions, okay. So it was what we call an optically thick medium, okay, it's opaque. The light cannot escape the interactions from these electrons and protons. Gradually the universe expands, which means it also cools, and the first atoms can start forming, okay. This period when the first atoms form is called as the epoch of recombination, and we think that happened at about 380,000 years, about 400,000 years after that T0. And this light that was bouncing off of these ions is finally free to escape from this interaction and comes towards us. So today we are able to receive this light from the very early universe, and we call that light the cosmic microwave background radiation. That really colorful green-blue layer, that is the CMB, cosmic microwave background, okay. So if your eyes were sensitive to microwave radiation, if you don't have an intuition, that's about 100 gigahertz or so, okay, in frequency, the sky would be aglow with a light, okay, and it's a very, very weak light. The temperature of that light is about 3 Kelvin. If you think of it as a black body, it's about 3 Kelvin. So if you go to outer space and you want to know what the temperature of outer space is, it is about 3 Kelvin, because the entire universe is filled with that microwave background. Okay, let's move on. So that happens to the light. What happens to the matter? We know that at some point the first stars have to form, right? Because today when you look out into the universe, the first stars are there. There are some stars, but at that point there are no stars and galaxies. At some point, and this is where the problem comes, we don't know exactly when and we don't know how the first stars and galaxies in the universe formed, okay? And that's what this talk is about. How do we go about trying to study those first stars? Okay, first of all, why is it important or interesting? Well, to me as an astrophysicist or cosmologist, it's a big piece of the missing puzzle. Like, you don't know what's going on. If you can't explain that part, your model of the universe is incomplete. Okay, for me it's interesting for that. But remember, it is these first stars that then explode, create the next generation of stars, to create the carbon that you and I are made of, to create the silicon this laptop is made of, okay? There was a starting point that started all of this, and these stars are key to that, okay? That's a more philosophical reason why it's important to understand. Okay, I won't spend too much time on this, but for those of you who have not seen this, please go take a look. I don't think we can appreciate how long 13.8 billion years is, okay? This is called the cosmic calendar. The Big Bang, T0, is on midnight, 0.00 hours of January 1st, okay? We are right now, December 31st, midnight, okay? Almost coming to the next year. So the entire 13.8 billion years is put on this calendar of 1 year. To give you a context, the first human beings, as we think, right, the early first Africans who migrated out, right, they came on the picture in this calendar on the 31st of December at 11:52 p.m. So humankind has been in existence for 8 minutes in the entire year. That is how old the universe is. I hope you can appreciate that context now, okay? We are trying to study February, okay, when the first stars formed. But did the first stars form on February 1st, 28th? What did they look like? How big were they? We have no idea. That's the problem. Okay, so I've just summarized the same thing. We don't know anything about the first stars, and broadly this period in the history of the universe is called the cosmic dawn, okay, because it sounds nice, it's appropriate. We think approximately it happened when the universe was about 100 million years old, okay? So like I said, February. Now, one obvious answer to this question is you build ever more sensitive telescopes. So you and I can see some things with the eye, we can see some dots, some stars. Maybe we can, if we observe close enough, we can see some Andromeda. You go to the, you see some point galaxies, right? But you can build a really huge telescope, and I think this is something everyone is aware of, the James Webb Space Telescope, right? This is the current most sensitive telescope, and it's in space. And this is what's called a deep field image, okay? So this, I don't know the exact number, but it has about some 30,000-40,000 galaxies. These are not stars. Each dot you see on there is not a star, it's a galaxy, okay? And this has been imaged by James Webb. So what is the furthest James Webb has seen? Does anyone know a number? You can throw a random number out there. You can tell me either in something what we call redshift or in terms of age of the universe. Any guesses? Close, 14 point something, okay? Yeah, but good try. That's the redshift, about 14.1, yeah. So here I put a bunch of questions. So I don't expect you to answer them, but this is what you have to think of, right? Because this is the most intuitive way to do it. You build a bigger and bigger telescope. So how big is the mirror of James Webb? Because that is the best telescope we have now in space, okay? We need to, what is the farthest James Webb has seen? We said it in terms of a redshift. We'll convert that to years. So how far do we need to see to go to study the first stars? Is it right? Can we see it with James Webb? And if you can't see it with James Webb, how big a mirror would you need? Okay. What is the biggest ground-based mirror that you have or it's upcoming? So here are your answers, okay? So James Webb has a 6.5 meter primary, okay? It's an optical telescope, so we all think, we have an intuition of optical telescope, right? There are mirrors, there's a focus, right? The farthest is seen, it's about 14.2 in redshift, which is a astronomy jargon of how to convert age to some unit, okay? And that corresponds to the age of the universe at about 300 million years. We want to go to at least 100 million years after T0, which is a redshift of 30. It doesn't sound like much, right? Just 200 million more years. It's not linear. It's not a linear problem, okay? We need about 100 meter large mirror, collecting area, primary mirror, to be able to see those first stars in space, okay? It's not practical. On Earth, on ground, there's an upcoming telescope called Extremely Large Telescope, ELT, in Chile. And that on Earth, with all the logistics that you can do, has a mirror that will be of 39 meters. Okay, so it's more or less impossible to actually image those very first stars and galaxies. So we use something else instead. I just told you that the universe is basically filled with hydrogen and helium. Hydrogen is very, very abundant. Okay, it's almost 92% of the gas in the universe is hydrogen. 8% is about helium. Everything else is barely nothing. Hydrogen, neutral hydrogen, has a very nice property. It's well studied. So it's a very simple system as far as me, as somebody who doesn't study hydrogen, is concerned. People who study hydrogen may disagree. It has a proton and an electron. The proton and electron can be positively aligned in spin or negatively, like anti-aligned, okay? So the anti-aligned state is a more favorable state. So naturally, hydrogen, with its own Einstein's coefficient, it has a time constant, will naturally go from a aligned to anti-aligned state if left alone. This is a highly unfavorable process, but it happens every some n million years. But the universe is 13.8 billion years. There is enough hydrogen. We have enough amount of this aligned to anti-aligned happening to be able to use hydrogen as a way to study the universe. And this is routinely done. We study our galaxy with hydrogen. We study other galaxies using hydrogen, using this signal. This signal, so when I say signal, this aligned to anti-aligned process, because there's an energy difference in the state, it emits a photon. That photon at rest frame has a wavelength of 21 centimeter or a frequency of 1420 megahertz, 1.4 gigahertz. Okay. So we want to use the 1.4 gigahertz emission from neutral hydrogen coming to us all the way from February, basically when the first stars formed, trace that process all the way to maybe March, April, okay, and see what's happening with all the hydrogen in the universe, and that will tell us the process of formation of the first stars and their evolution over the first generation of stars. And that's what we do. So we no longer are talking about optical light and optical telescopes and mirrors. We are now talking about radio telescopes, okay, operating at radio frequencies. Okay, this signal from the first stars, the 21 centimeter redshifted hydrogen from the early universe, from the first stars, has not been detected. So the title of my talk was how we can detect them and not how we have detected them. This is an unknown open problem that many groups across the world are working on and trying to detect this 21 centimeter signal from the early universe, from the first stars and galaxies. The signal is very, very weak. I'm going to tell you a bit more about the problems about why it has not been detected, even though people have been trying for at least 25 years. Okay. So, some clues about the signal. We are thinking about the average evolution of hydrogen in the universe and how that changes when the first stars come into the picture. So, this signal comes to us from all directions in the sky. Some people try to do some more specialized, this direction, that direction, but for this talk, the signal we are trying to look for comes from all directions. It's not one star here, one galaxy there, no, okay? So that's an advantage. The second, the frequency range has now redshifted, okay? We are all familiar with school, high school, college, Doppler shifting, right? Doppler shifting is because of velocity. Cosmological redshifting is because the signal itself gets kind of stretched when the space-time expands, okay? There's a subtle difference in why the redshifting happens, but the formula is more or less, okay, the same. So what was emitted at 1420 megahertz gets redshifted to you and comes to you at a lower and lower frequency. So based on how far the redshifted signal comes to you, the signal can be anywhere between 10 megahertz to 200 megahertz. It's a very, very weak signal, partly because, well, it's coming from far away, okay, and partly because this is a forbidden transition. We measured power in terms of temperature in radio astronomy. It's jargon, it's a convention. So the signal that we are trying to detect, I've put some numbers here, but we can work out the details later. The order of magnitude, the temperature equivalent of the signal amplitude is about 10 millikelvin, and over a frequency or a bandwidth of 1 megahertz, the kind of power we are trying to measure is 10 raised to minus 19 watts, okay. That's 1/10 of a billionth of a billion watts, okay. That is how faint a signal we are trying to detect to see that signal. When I keep saying signal, what is it that I'm trying to study, right? This is what it is. I will quickly go over what the x and y axis are, but I'll tell you the takeaways, okay? And if you want to chat more about it, we can talk later. X axis is that redshifted frequency. Y axis is if I give you an equivalent temperature for the signal from neutral hydrogen, that spin flip transition, right? The 1420 megahertz signal amplitude. If I give it some equivalent temperature units, and I see that I'm looking at the signal with the cosmic microwave background as a contrast. It's a differential brightness temperature, okay? And you see some interesting features, it goes up, goes down. That contains the actual details that we want to study. Each of these curves is a simulation of what that signal could be like, okay? The kinds of information that we are able to interpret from this curve or any one of these curves is when those first stars and galaxies formed, they emit Lyman alpha radiation, okay? How strongly coupled was this Lyman alpha radiation to the 21 centimeter signal? When did they start going, say, supernovae? And when did they start emitting X-ray radiation? How strongly did that X-ray radiation heat the hydrogen gas? And when did the entire neutral hydrogen in the universe become reionized? We have other ways to confirm that when you look at the universe on large cosmological scales, we no longer have much neutral hydrogen left. Excuse me. It's mostly ionized hydrogen, okay? So this curve will tell us all of that information. Each of this has a slightly different parameter put into it, and the name of the game is you have to find which of this is the real curve, okay? And maybe there is something completely out of the box I've not put in and it's a different signal, okay? So this is how clueless we are about that process, and that's why it's a very interesting topic to work on. So other takeaway is frequency range. I told you. I've zoomed in on the part that goes from 55 to 200 megahertz. There's another signal also at lower frequencies. And the y-axis, order of magnitude, it's about 10 to 100 millikelvin. It's negative because I'm looking at it in absorption, okay? I'm doing some A minus B, and if B is greater than A, I'll get a negative value. Now, this is an analogy that I find helpful. You drop something in a water pond or something, it creates some ripples, waves are going away, so it creates a faint disturbance. Imagine each of these drop, the thing that you're putting in is like a star, the things that are moving away, that you're trying to study the object that fell into the water pond by looking at the ripple. So we are trying to study the first stars by looking at the hydrogen, and it's a very small faint ripple. This is what our galaxy does. This is like an ocean, huge tidal waves, that's how noisy our own radio emission from our galaxy is. Okay. So, I basically said what I wanted to say, so I won't repeat it. So these are all the challenges to why this signal has not yet been detected. Okay. First is a very fundamental challenge. We live inside a solar system. Solar system sits in a galaxy. Galaxy has synchrotron radiation. Okay. There are electrons that are getting accelerated in magnetic field lines, and that creates synchrotron radiation. And over this frequency range, about 100 megahertz, that's very, very bright. Our galaxy emits radio waves. Okay. And that was a discovery of kind of beginnings of radio astronomy. That's how it was discovered. Okay. That galaxy emits radio waves. Those radio waves are 6 orders of magnitude, 1,000,000 times stronger than the signal we are trying to detect from the first stars that comes to us from beyond the galaxy. On top of that, we have other problems such as our own ionosphere creates refractive effects, absorption, reflection. So at radio frequencies, it is like a disturbing medium for you. Then to top it all off, we have human beings who create loud radio noise. This frequency range, if anyone knows, 94.3, 95, that's the megahertz frequency of transmission of these radio transmitters, FM radio transmitters. And there are megawatt transmitters across the world, okay, it's huge, okay. All of this creates noise. So this is an actual measurement. X-axis is frequency, y-axis is some power level. And you see all those spiky lines, that is human-made terrestrial radio frequency interference. So these are all the challenges. And just to give you a picture of what our galaxy looks like in radio, this is a image probably at some low frequency, maybe 100 megahertz or so. The way to read this is like a compressed projection of a sphere, the sphere being our galaxy. The center point of that ellipse is 0, 0. 0 latitude, 0 longitude, okay. We sit somewhere along the galactic plane to the right, and in astronomy, east and west convention are flipped. Top is north, bottom is south, right is west, left is east. Okay, so we are sitting there, and of course, over order of maybe 100 million years or so, we take a orbit around the galactic center. Okay, don't quote me on that time scale, but we go around the galactic center. So again, on the right side, these are all those curves that we are trying to detect at the bottom. What our galaxy emits is way up there. So we have to find that ripple of the hydrogen because of the drop from the first stars, and we're looking through an ocean. Okay, that is the problem. Now, what do we do to actually make this measurement? We build a radio telescope. For those who have not seen it, you have dish antennas on your terrace. There are many of dish antenna type radio telescopes, huge parabolic dishes. We have a few in India. There is a telescope called GMRT's of Pune. So it's among the premier radio telescopes in the world. We don't use those kinds of telescope for this experiment. We use a very custom telescope because the problem we're trying to see is different. Most radio telescopes will want to look at one galaxy there, one pulsar there. So they need a huge collecting area with a small antenna beam that they can point. We, on the other hand, we want a large beam. We don't want any localization because our signal comes to us from everywhere, but it has to be very, 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 very sensitive. So the entire detail is in the calibration, how you take that power, convert it to the right units, remove all your instrumental effects, separate the foregrounds and find that signal. So you have an antenna with a beam, it sits on some surface. You have some analog receiver, basically RF electronics, amplifiers, filters, some noise injection, calibration. It goes to a digital receiver, FPGAs, GPUs, etc. That gets collected as data, and you look at and analyze that data. So there are many experiments. Well, actually there are 5 experiments across the world that are trying to do this. We are one of those 5 at RRI. We have a ground-based experiment called SARAS. These are some pictures of different versions of SARAS. SARAS has gone to Ladakh, it has gone to some places near Anantapur, Gauribudnur, another Ladakh, Sharavati, recently Andaman. So this is a portable, high sensitivity calibrated radio telescope. So the way we work is we take the telescope, we spent months if not a year designing every detail of this telescope, testing it in the lab, getting it to make sure that it has the necessary accuracy and precision for our experiment, sensitivity. We pack up the entire experiment including the antenna. Antenna is this big, put it in boxes, ship it, go out as an expedition, spend 3 to 4 weeks on the field, put up tents, put up batteries, generators, solar panels, and every night we run our experiment, and after 3-4 weeks we pack up everything, come back and analyze the data for the next 6 months. Okay, we've been told that a good way to describe this mode of experiment is that we are nomadic astronomers. Okay, so later I'll come to why Saras right now floats on water. But here are some nice pictures. So this is what it involves. You have an antenna that is an extremely unconventional cone-like thing sitting on some plate floating on water. A cable comes right below that, in that yellow structure that you see below that cone. You have an analog receiver that does a lot of the important calibration that I mentioned, amplification, noise injection, calibration details. Then 2 optical fiber cables come out along the water surface to a box that sits on the land that has all the digital electronics, digitization, correlation, spectrometer, etc. Now, this is what life can look like as an astronomer should you choose to be one. It sometimes involves sitting on a boat in the middle of nowhere, trying to do some jugaad with wood. Okay, so this is our team doing an deployment in Andaman, and there is a picture. Okay, I think you can see those little yellow buoys floating along the water. That is the cable going back to the shore from the antenna. And this is how fancy the setup is to protect it from rain. You put it in a tent and you sit in the tent and work. Okay, now, so these are some places we have been to. We have gone to Andaman, Ladakh, few more places in Karnataka, and last winter a team member from RRI led India's first winter expedition to the Himadri station in Arctic, Svalbard. He was so our team member went and did RFI survey for Saras as well as Apsara. RFI standing for radio frequency interference. So when you go select a site, you have to go to a place that is not that radio loud. Okay, it is relatively radio quiet, not too many FM transmitters, not too many telephone signals, whatnot. Now, why does Saras float on water? Okay, here are some problems that come practically. Okay, so I showed you the simple version of that picture. This is the practical version. This is reality, and this is why the signal has not yet been detected. Everything highlighted in pink are things that are just you have to figure out in your experiment. You better do a good job. You better write good code. You better do your data analysis well. You better take care of your antenna design, all of that. But there are 3 things that are unique to operating an experiment like this on Earth. Okay, we talked about 2. One is radio frequency interference, which is human-made loud radio noise that contaminates your data. The second is ionospheric effects, which can refract galactic signals. The details of this are little, I won't go into it now, but the idea is that you're looking for a signal that comes to you from beyond the galaxy. Your galaxy is very bright though. And if you have refraction, it's like you have different parts of the galaxy coming into your data at different frequencies. And that creates confusing artifacts, and you can no longer tell which part of your data is coming from your galaxy and which part of it is coming from the cosmological signal. So that's why refraction is a problem. How much of a problem has not yet been determined. It's an open problem. But what we do is we make sure we know the total electron count, or what they call TEC, which means we have a quiet ionosphere. And on those nights we observe. We don't observe during the day. We don't observe during solar flare going off, and that's disturbed the plasma and the ionosphere. Okay. The third problem is that when you have designed an antenna to do the right thing, behave perfectly for your requirements, you do all the simulations, there are electromagnetic softwares and solvers that do this for you, and you stick that antenna on soil, you stick that antenna on water, right? You stick that on any surface, right? The properties of the antenna change, because antenna is not just a piece of metal, it is finally currents flowing on a surface that you tap out at a point as a voltage. Okay, so if you put it on a surface like a dielectric, which is earth is a dielectric, soil is a dielectric, based on the things like how wet that soil is or how stratified the soil is below the top layer, your antenna properties will change. And that is a problem that is close to impossible to model accurately and extremely challenging to measure in the field. Okay, but a good way is to at least go to a low stratification medium like water. Okay, so unlike soil whose properties can keep changing, you go to a stable water body like a lake with a known salinity, you can design an antenna for that and stick it on there and take measurements, which is why Saras has gone to water. But a better place is to go to the far side of the moon. Okay, there have been measurements by experiments in the past at lower frequencies that tell us that the far side of the moon, the side that you do not see because of tidal locking, is radio quiet. So the moon is basically a blocker of terrestrial radio emission. Okay, so you can go to the far side of the moon and you can go in orbit. So you address all the three problems that we worried about. So first of all, there is no RFI because there have been measurements and simulations that tell you there is no RFI. Secondly, there is no ionosphere per se on the moon. And thirdly, you can operate in free space. So you are not sitting on the lunar surface or soil. You are not in the vicinity of some other medium that can distort or change your antenna properties. Okay. So keeping this in mind, our group has proposed an experiment called Pratush to ISRO as part of announcement of opportunity, and we were successfully awarded a seed fund, like a grant, to develop a concept model of Pratush. So this design was arrived at after we got that seed funding. So this is a summary of what the experiment will look like. We are focusing on 55 to 110 megahertz frequency range. That conical gray structure and the funny thing below it, the umbrella below it, is the antenna. But we have to do this antenna design keeping in mind the satellite itself, because then we don't repeat the same problem. I design an entire antenna and stick it on a piece of metal and say work the way I expect you to, right? So we have a CubeSat dimension bus we have assumed, and keeping this bus in mind, we have designed this antenna to have all the right properties. For us, the right properties are things like having a large beam that doesn't shift too much as a function of frequency. And the way the antenna connects to its electronics is known, basically the antenna's response function, or for those who know the language, return loss, is smooth as a function of frequency. All of this is to make sure that you are able to eventually separate your galactic emission from the cosmological signal. That's what determines the antenna design. It has all those properties in the presence of this bus. Okay. Inside the bus, you have the spacecraft electronics, payload electronics, digital electronics, analog, etc. There are some things, open problems that we are actively working on about Pratush. First is choosing the right orbit. We have some clues. We want to maximize time on the lunar far side without it seeing the sun and the earth, but it has to keep coming back towards the earth to downlink the signal to us. Okay. Second, we have to figure out a way for this antenna's metal to not warp, because this antenna is going to see thermal swings of 500 degrees. It will go in and out of the sun, right? And there is no atmosphere to moderate the temperature swing for you. So it's a material science problem we have to look at, right? What type of material with low thermal coefficient of expansion, right? And the third is an EMI shielding. So your own electronics are also going to create noise. Okay, you don't want to go all the way to the far side of the moon only to be seeing your own emissions. You want to look at the galaxy, you want to look at the signal you're trying to find. So the way you protect and design your electronics so that your antenna doesn't pick up EMI at the levels you care about is another problem we are working on. That is also a combination of electronics, EMI modeling, as well as material science. Okay. So what we have done is, instead of saying, okay fine, clearly we know there are not enough launch opportunities for this problem, whereas there is an active Chandrayaan program and we have been trying to get our spot in there, we can try to see if we can do this around Earth to some extent, because 2 of the 3 problems get solved, right? You can go above the ionosphere, you can go to free space, but you will see RFI, you will see terrestrial emission. But how bad is the RFI? Are there pockets of RFI that are RFI free? We are trying to see. So this is what Pratush is like in the lab now. So right now we are powering it with batteries. Eventually there will be some solar panel equivalent. All the electronics can fit on this table and the antenna is this big. The antenna size is determined by the frequency range of operation. I cannot, for the sake of flying it to space, make it a smaller antenna. It will not be an antenna at this frequency, right? So, excuse me. So this is a kind of estimate we have done. All the signals in blue, right, are signals we think we can detect in Earth orbit if all the other conditions are right. This combination of blue and red, so most of the signal space is something we will be sensitive to on the lunar far side. So this is why we're taking like a more programmatic approach and say, let's try it first around Earth, at least we'll get more launch opportunities. It is a less complex and less expensive compared to a lunar launch, and then eventually go to the moon. We are not the only ones who are trying to do the lunar far side experiment. There are every space agency, NASA, ESA, JAXA, the Chinese guys, all of us have at least 2 or 3 such proposals to try to go to the far side of the moon for radio astronomy, because we know that is where things are radio quiet. There are very few radio quiet locations left on Earth for very low sensitivity. And interestingly, below 10 megahertz, you don't see radio emission anyway, because your ionosphere reflects and blocks all radio emission below 10 megahertz. So if you really want to study anything about the universe and the galaxy below 10 megahertz, you have to go to space, which means you better go to a radio quiet location in space. So there are many competing proposals across space agencies, and it is a very tight race. So in that spirit of simulating the RFI around Earth, this is other kind of work astronomers do, well, if you can call it that. So we have models that simulate what is the terrestrial radio frequency interference that come from FM stations. So we built a global model putting in every FM transmitter across the Earth, and wherever there are gaps, we fill it using statistical models, and we think there is a clean patch kind of around the Antarctic where we may be able to get some decent radio noise free time, okay, RFI free time for such an experiment. So we want to go and actually measure this radio free part. So we have someone who is building a small payload. Right now that's just a concept, but really small, like a CubeSat type of payload that just will go and measure the RFI around Earth. This is not going to have the sensitivity to detect the final signal, but it will go and tell us what are the power levels of RFI across different points of Earth from space, and that will inform whether we can actually confidently go ahead with a low Earth orbiter full sensitivity experiment, or the only way is to go to the far side of the moon. So that's the last slide of my talk. This is the summary. I hope you got a flavor for the fact that if you really want to study the first stars and galaxies, you have to use hydrogen. You can't really be building an imaging type of a telescope. We do this at radio frequencies where there are lots of other problems. So a lot of the problem is in designing a really good, high sensitivity, well calibrated single radio telescope to look and give you all the information you need to know. And this is important because that will give us a complete picture of our current universe. And also, like I said, eventually you have come from those first stars too in some sense. So it's a nice problem to think about. So I'll take questions. Thank you.
So in the first that you showed,
yeah,
the what do you call the area, the satellite?
Pratush, yeah, this.
Suns,
yes. So it is very small thing.
Yes.
But in Kodaikanal observatory, the telescope is very big.
Yes.
So what's the difference?
So first of all, Kodaikanal observatory is a radio observatory, so it has different design metrics. But I can tell you, compared to generally a radio telescope, we don't want a traditional radio telescope because the kind of signal we are trying to find is not a traditional signal. So we are not trying to look at one direction of the sky with a large dish, but we want, more importantly, like I said, the antenna beam of that telescope should be very stable over the full frequency range, and it should be like a badly behaved antenna across the entire frequency range. It's not a resonant antenna, because resonance introduces funny shapes in your data that you can no longer use for analysis. So it's a intentionally unconventional telescope, and we do what we call as absolute calibration. So most radio telescopes look at a different radio source in the sky and derive the calibration. We calibrate our telescope to go from whatever digital units to a temperature value, and that is a priority for us because we want to get the temperature. So that's the main difference between this type of telescope and the other radio telescope.
Thank you. One more question. So you mentioned that new stars are born and sun is also burning.
Yes.
So suppose sun burns out.
Yeah.
Will there be any other star coming up that can sustain life on Earth?
Well, we will be long gone by then because the sun will grow into an envelope that will absorb the Earth. So Earth will be gone, or habitability of the Earth will be gone when the sun dies. But we don't think new stars are born in the same location where the old stars are born. So even in the local universe, the star formation is an active research area to see what makes a star and not a Jupiter. Jupiter came very close to being a star. So but we don't think a new star will replace the location of the sun. It will happen somewhere.
So ma'am, as you said that finding about the first stars is like finding the source of the ripple that is spread through an ocean.
Yeah.
So the ripple is basically a 2D acoustic wave, the ripple.
Okay.
And the droplet would be the source injection. So there's been work like using physics-informed neural networks called the inverse problem, where we have the data, observe values of the ripple, which is like at the receiver, and we measure the pressure, and we estimate where the source location was. So looking at this analogy, what data are we looking for in the form of as we are saying, the ripple is a 2D acoustic wave. So what data are we looking for exactly, apart from the radio waves, for the estimation of the first stars?
Okay. So first of all, let me clarify that that was a very bad analogy because what we're looking for specifically in this case is not an acoustic wave. Okay, we are looking for standard electromagnetic TEM, transverse electromagnetic radio waves. That was just an example to tell you that we are using hydrogen instead of directly looking at the stars. Okay, and just to show you the order of magnitude of the noise. Okay. Coming to the what other probes, what else can we use, if that's the question. For the very first stars, there's honestly nothing much else we can use other than hydrogen. For the later stars, the part where the first stars start dying, right? Okay. So maybe from the point where the graph starts, let's look only at the black curve. From the point where it starts to where it comes down, there is nothing else you can use other than hydrogen, this signal. Okay. From the part when it starts going up, right, you can use telescopes like James Webb. It goes close enough to that point. You can also start looking at X-ray radiation because these are X-ray sources heating the gas. There's there's something called the Lyman alpha forest, which is basically looking at the Lyman alpha signal, but you need the first star to have already formed for that. Okay, you can look at the Lyman alpha emission coming to you through pockets of neutral hydrogen to map something about that star. But the very first stars, that period, you can't use anything else. But please don't keep in mind the analogy that it is an actual acoustic wave. It is a TEM wave that is just to get you a feel for how problematic the detection is. Yeah.
I have two questions.
Yeah.
So initially my first question is, in Pratyush experiment you were saying that you needed a material with low coefficient of thermal expansion.
Yes.
So what was the material you used and how was the fabrication done?
So right now we only have the laboratory model, we don't have the flight model. So that is an open problem we're working on. So in the lab we just use aluminium. We use aluminium for all our telescopes. We have been told we can consider carbon fiber reinforced plastic with strips of metal because you do need a conductor. But I believe CFRP is a material people have looked at which is reasonable at doing this because this is not the only experiment that has done orbiting. But our constraints on the amount of distortion, warping we can tolerate is very, very low compared to other telescopes where, other just communication antennas, our requirements are very stringent. So we are looking at this a lot more seriously, but that's a possibility, CFRP. Yeah.
In Cirrus and other parts, the parabolic antennas or horn type antennas are there.
Yeah.
Oh.
Yeah.
And why don't you try for microstrip antennas?
This frequency is very low for a microstrip antenna. So typically microstrip use at few gigahertz. A microstrip, people have been looking at it, but yeah, it will be like this big microstrip first of all because it's a meter wavelength frequency range. It will be huge microstrip. And secondly, we worry about some losses is one problem. And the third main problem is, like I said, our requirements of the antenna is this beam stability as a function of frequency and return loss values. So we have used microstrip antenna at a higher frequency experiment with the same requirements. It is just more practical. The antenna operates at 2 to 4 gigahertz. The antenna is like this big. But it's more a problem of fabrication of a PCB this big, more or less.
So I'm unsure as to how quickly the temperature change happens for the antenna.
Oh yeah. Okay.
What if, since the window for your temperature change and your distortions is very small, how about you use two antennas, one for the cold side when you are inside, when you're on the dark side of the moon, and one for when you are facing the sun?
See, partly it's because you're going to be orbiting. You cannot if you have to orbit to get your data out also, right? There are some telescopes that are planned as landers that will always sit without seeing so much of a thermal shock. But remember, the moon has a 14-day period. So every 14 days, sun will rise on the moon. So at some point, the sun always comes to the far side. The far side is not a dark side like it's popularly thought. At some point after 14-day cycle, sun will come even on the far side, everything will get hot. So there is no escaping that heating cooling, even if you put two, because things go round. So that's the problem.
If there are no more questions, so let us thank